So my name is by discussion. It is my pleasure to open this afternoon session, and the first speaker is Alexander Litvak from Alberta. The title is here: the minimal dispersion of in the unit.
Okay, thank you very much, and thank you very much, organizers, for inviting me here and giving possibility to speak. So my talk will be based on three works. Myself with Andrea Ermak and with Galina Lifshitz, and I will discuss minimal dispersion. But first I will review previously known results, or results which were done in parallel. And I also would like to mention that some of you heard very similar talks, mine, and but there will be some new results here. So what is minimal dispersion? It's very easy to formulate the problem. So we start with unit cube in RD, and we want to solve the problem, the following problem, that we want to find configuration of n points in such a way that whenever we consider rectangle with axis parallel, meaning that all facets are parallel to coordinate subspaces, some point should be inside. So of course we can formulate this. Well, such number we will denote by n epsilon z, and of course we can formulate it equivalent problem, which actually is called dispersion. So here I fix essentially some epsilon and d. Epsilon will correspond for volume, and I'm looking for n. But I can fix n and d, and to find the largest possible epsilon, such that for any configuration I can find axis parallel box such that no points inside. So this is just an inverse function. So this will be our setting. Such second formulation is called minimal dispersion on the cube, of course, and denoted by this. And our goal to investigate these functions when epsilon goes to 0 and d goes to infinity. So this I want to emphasize that this is function of two parameters, and I want to understand behavior as function of two variables, not fixing one of them. There are a lot of works when people fix one of two variables, and actually I will say that if one variable is fixed, we more or less know the behavior. And also I would like to say that there are many works in this direction. Of course I mentioned works which are related to my talk, but there are many other works which I don't mention, and in particular there are many works in dimension 2 which I don't mention. There are several works on behavior of certain lattices or certain configurations by Vladimir Temlyakov, by Mario Ulrich, by David Crick. I'm not going to mention. So here is formal setting. So by this R, we will denote all axis parallel boxes, which is just product of rectangles. Then dispersion of a given set is just maximum volume of box from here, which doesn't intersect this set. Then minimal dispersion is just infimum of over all sets of cardinality n, so we have n points. It's exactly what I explained before, just formal writing. And then the functions that which will be easier just for presentation. Of course, I can rewrite all my results in terms of the dispersion, but it will be easier for presentation to investigate function n, which is just inverse function. And once again, main goal to understand behavior as function of two parameters. And then I will start with describing known results in paper of Roth and Tische. There was bound, which essentially was d to the d, which was slightly improved later by Larcher to the 2 to the 7 d plus 1 over epsilon. This one of first bounds. And very recently, Buch and Chow managed to improve this actually significantly to the polynomial bound here. And it should be compared with lower bound, in particular with trivial bound, which is written here. Why it's trivial? Because I can split my cube in n+1 parallelepipeds, and of course, if I have n points, one will not contain. So bound 1 over n+1 is trivial. So essentially, bound, which is here, is trivial.
But you can take different directions.
It doesn't matter. I will get the same bound. Yeah, of course, I can split it in many places. Just lower bound and trivial lower bound. Yeah. And there was work of Dimitriescu-Jung, who slightly improved. It's already much less trivial to get here constant larger than 1. But for me, constants are not important. So for me, it's more or less the same result. What is more interesting, from their work, it follows that if I send epsilon to 0, then epsilon times n will have limit, which let me call CD here, but I will use CD for different reasons. So if we send epsilon to 0, then we have such limit, and of course it's interesting to understand what is CD. Say from this bound, it's clear that CD is less than d squared log d. And on the other hand, if we fix d, so if I want to fix d, then behavior we know it's 1 over epsilon. I actually like to present, probably will have this picture. I like to present, I will use another. Like to present dependence between epsilon and d in the plane. Here will be 1 over epsilon, here will be d. So if I fix d, so say d is a constant, then we know that in this part of the plate behavior is like 1 over epsilon. Everything up to absolute constants. Absolute means that it doesn't depend on any other parameter. So it's just number. Continuing with lower bound, it was quite big achievement in 2017 to show that in fact n epsilon d grows with dimension. So it goes to infinity as d goes to infinity. And also in the same paper of Buch-Chow, they proved that if epsilon is extremely small will be for me something like this, then actually this logarithm can be improved to d. So combining these results, what I already mentioned, we can say that n epsilon d is less than this bound, 1 over, well, if I want bound like 1 over epsilon, then here I can put logarithm d, and here I can put d squared log d. Also, if we discuss limit, then limit is between d and d squared log d. So still there is gap, but it's not very big, not like here. Here is difference between logarithm and polynomial. And also from their methods, they also have 2 steps. One step gives d log d, and second step gives d. They suggest that probably the correct bound should be d log d. But we don't know this. And like I said, that there is some gap in this bound when epsilon is not very small and d goes to infinity. So what is known in this direction? There was an old paper by 4 authors which essentially implies such bound. They had much more general setting, and they gave a very general estimate for some learnability which can be applied to this problem, and their bound was in terms of VC dimension, which is in our setting is 2D. So their bound can be formulated like this, and here we already have better power of d, but the price is that we have logarithm 1 over epsilon. That's why I say that there is a huge difference between extremely small epsilon and not so small epsilon. Rudel gave direct proof of this result using just random points uniformly distributed in the cube. So this holds for random points when I just use ID random variables with respect to Litvak measure on the cube. And also I want to mention, which I already probably said, that this bound is better if epsilon is not extremely small, meaning that epsilon is larger than d to the minus d. So, so it was natural to conjecture, and it was conjectured at some moment, that n should behave as d over epsilon. But later it was proved by Sosnovets that in fact, if you don't care about epsilon, then dependence on d is logarithmic. So, so if I fix epsilon in this plane, then I know that in this part it should be some logarithm of d. Question, of course, what happens here, that's what I want to discuss. And just few remarks. And dependence on epsilon in original paper of Sosnovets was, well, actually it was terrible, but it was almost immediately improved by Mario Ulrich and Jan Wiberl, who used more or less the same idea, but much more careful and delicate calculations. It was like this with logarithm square, and then I use something different, slightly different approach to remove this power. So we have bound here, and which corresponds to this constant. And just to say that, well, if you forget about logarithmic factors, that this bound is better than previous bounds if epsilon larger than 1 over d, essentially. So I probably will put it here, so my picture. This is essentially d is d double log d over log d square, yes. Then here we have that it is less than what c over epsilon square log 1 over epsilon cd. Here also logarithm d. Oh, just one. Logarithm 1 over epsilon and logarithm d. Of course, this epsilon square, well, most people believe that it's not needed, just byproduct of the proof, but actually very recently this year in this paper they proved that if epsilon is not very big, as 1 over square root of d, then we do need epsilon square if we want to have logarithm of d. So in a sense it means that we cannot improve both together. We cannot have logarithm of d and together with 1 over epsilon or even with logarithm. So essentially it's here, and this is this line is essentially square root of d. So here we have that it's also larger than c epsilon square. Well, they have logarithm 1 over epsilon here and logarithm d. So more or less in this part, at least in this part, we know the result. And also before I mention our results, I would like to mention, just to mention several simple facts. Well, not simple facts, but I start with simple facts about very large d. So if epsilon is larger or equals than half, then just one point in the middle, of course, enough. So if I take this point, then any box of volume larger than half will have this point, which is trivial. What happened between half and quarter? Well, Sosnovets in the same proof, in the same paper, he proved such result. So what is interesting for me, at least here, that it doesn't depend on d. So upper bound, if epsilon larger than quarter, doesn't grow with d. It bounded by some function of epsilon. So just combining with previous results that I mentioned, if epsilon say between quarter and 8, we have just logarithmic in z estimate. Also, this bound was slightly improved by McKay. So he just improved dependence. He put square root of epsilon minus quarter. Still don't know is it sharp or not. Especially that his construction and actually Sosnowiec's construction, they took points on diagonal. So of course, probably we have much better configuration if we stick out of diagonal.
So could you remind us, this capital N of epsilon and G, so what is it?
It's a minimal number of points, such that there exists configuration.
A minimal number of points?
Yes. Such that you can find configuration, such that any box of volume larger than epsilon contains at least one. Yes. So, probably what I said, I need to put here also one line. It should be like this. So it's essentially d to the cd, like I mentioned. Here we have result of Buch-Chow, which says that this is less or equal than d squared log d over epsilon, but also large, well, larger I will say probably later. And here we have result of Rudolph, which follows from previous also results that this is d over epsilon log 1 over epsilon. Something like this, which I wrote here. And now I'm going to present something new. So it's a result from my paper with Arman. We essentially reduce this logarithm of 1 over epsilon to double logarithm. So in the plane, it would mean that we have here something like e to the d, where result of Buch-Chow is still better. But here in this region, we have better bound, which is essentially d log 1 over epsilon. And a few remarks about this bound. First, I say that it's based on at least two of my papers, one with Arman, second with Galina Lifshitz. With Galina Lifshitz, we use random choice of points, and we got logarithm here. So the first term was the same, but additionally we have logarithm 1 over epsilon. And this was almost sharp result, because in the paper of Hinrichs, Krieg, Kunsch, and Rudolph, they proved that if we use random choice of points, then the lower bound, is like this. So up to double logarithm here, it is sharp. Moreover, if epsilon is smaller than this, then we should have logarithm. And in fact, it's a property of Lebesgue measures that whenever you put random points, you still will have holes. Even you can see it even in one-dimensional case. So on the segment, if you put random choice of points, then you will have some large segment, and how large it's more or less of this size. While, of course, the best configuration will be just to split in n equal pieces. So, which shows that random choice of points is cannot be best possible, and also this bound, of course, shows that our bound cannot hold for random choice of points, because when epsilon goes to 0, this bound becomes much better. And yes, and just to I put here the results to compare. So with this we just have double logarithm. With this result, well, it's difference between, we don't have d squared, but we have double logarithm. So cool, more or less this picture response. I also probably should put that in this part we know that it's larger than d over epsilon. Well, this part. So here I just put this picture and new bounds. At least for this moment, it's what happens. And now I want to discuss some ideas of the proof. And I start with ideas for random choice of points, which were used in many papers. So what should be done by simplest possible method is we will consider random points independently, of course, chosen independently, uniformly chosen from the cube. And what we want that each box of volume epsilon contains at least one point. So we cannot check all boxes, so we will use kind of nets, so which I will call test boxes. So they, what we want from them, we have some set, and we want to say that it's enough to check all rectangles in this set. If each rectangle here contains points, then each rectangle in my set also contains point. Of course, the easiest way just to think about it is that for each rectangle here, I can find some rectangle here which is inside. It's not for all cases, but for most cases we use this idea. And then we just apply union bound, because how to estimate probability of bad event that that not all of them can, well, bad event that some of them contain no points. So there exists rectangle containing no points. We estimate using union bound that sum of probabilities that given rectangle contains no point. And this is more or less standard technique and standard method. So here we need to find balance between size of the net, because we will multiply by size of the net using uniform bound, and probability. What is good about this problem and this setting is that computation of probability is very simple, because we need to just to find volume and of rectangular box, which is just product of lengths of sides. So it is very easy. So what is not easy is to construct the set of test boxes. So this is main part, and Rudolf used some construction which which used for something else, and we improved this because we constructed new set of test boxes which fits exactly this problem, not some other problem. And another part which I want to mention, and I will explain, that like I said, if you just use random choice of points, it will not work. Well, it will work, but it doesn't give good result, good enough result. So what we will use two steps. So first we choose random points, and then we use, in a sense, non-random step. We will fill out boxes which are not, which do not contain points, random points. Actually, this idea was used in several works in combinatorics, but somehow it wasn't used for this problem. I don't know why. So what we will do, our approximation will be like this. So I will denote by B epsilon z the set of rectangles inside the box such that volume is larger than epsilon. And so our initial set, well, set that I want to consider as B epsilon z, and I want to say that my set of test boxes is delta approximation for this set. If for any set from here I can find rectangle from my N such that this rectangle is contained in B and volume is larger than delta. So I need to control volume and I don't want to lose too much, so delta will be very close to epsilon. Otherwise I will get bad bounds. And lemma, well, lemma that substitute probabilistic lemmas that used before by Rudolf or by in my paper with Galina Lifshitz is like this, that if we know, if we can construct a set of test boxes of certain cardinality, then my dispersion is bounded by logarithm of this cardinality times delta over delta. So improvement here is exactly because we add a non-random step. If we don't have it, then lemma proved by Rudolf and variants of this lemma proved in later papers would give this bound. So the difference is having delta inside, and it is crucial to remove log of 1 over epsilon. So I will say, I will show a proof very briefly because it's, well, it's relatively simple. So we take m random points, and then we want to check how many boxes do not have this point. So by bet event we denote EA. It is even that A doesn't contain any random point. So in some papers it is called empty box, empty because it doesn't contain a point. And then we count how many such points we have. So it's sum of characteristic functions of this event. And then we just compute expectation of this number, which is easy. Once again, to compute probability here is easy because we deal with Litvak measure. So it's cardinality of set, and each box here has at least, measure at least delta, so it's 1 minus delta to the n. So because of it, there is realization of random points such that my all rectangles from here except such number will contain random point. And then I just choose 1 point from each such rectangle, so my bound is here. And then I optimize with m. So this gives slight improvement, which is essentially this delta, which is important. And just one remark that in all previous papers we estimate that each box contains at least one random point, which would correspond that we estimate probability that L is 0, which is even easier. So this is improvement in bound, and now I will say I will give idea of how to construct the set of test boxes. So this idea comes from our paper with Galina Lifshitz. So we identify each box. We will it also will be in 2 steps. So first we will consider so-called uncorked boxes. So one corner will be 0, and then I will consider boxes of volume epsilon. Of course, because one corner is at 0, each box just corresponds to, well, I can identify each box with upper right corner, so just with one vector. And I also can fix that I consider only boxes of volume exactly epsilon. I don't need to consider all larger than epsilon. And then I will consider this set. So what I have with volume epsilon, I have such boxes. Something like this. Yes. So picture is like this, and my, over here, my points B with what I correspond, they lie somewhere here. So I will consider set of such points. I introduce one additional parameter beta. Beta will be either 1 or 1 plus something small. And then what I need to construct. For each such set, I need to construct a certain finite set such that, well, boxes are inside, so they are smaller. I probably should use different color. So they are slightly smaller, so it's epsilon to the power 1 plus gamma. And property is that if I have box from here, I can find box inside. So geometrically, it is here. So for every set from AD of epsilon, just volume epsilon, I can find from n0, volume is epsilon to 1 plus gamma, such that all coordinates are smaller than corresponding coordinates. And condition on coordinates here is product equals to something, product is fixed. Of course, with product it's not very easy to work, so we will apply algorithmic function to pass from product to sum. So we will apply this function, so f of t is essentially logarithm of 1 over t, normalized with ln of 1 over epsilon. And we consider function of capital epsilon, which sends such vector to such vector. So I apply this function coordinate-wise. And what it gives me, well, it's like I said that instead of product, I will have sum. So geometrically, well, it is first it will be bijection, but geometrically it will send my set to the simplex in RD, but I of course produce only two-dimensional picture, so this is my RD. And my points will lie, well, on hyperplane. If beta equals to 1, it will be hyperplane sum of x1 equals what, to 1, and also all xi are positive. So there is, this is simplex. Well, it's not segment, it's simplex. And this is my initial set. And what I want to cover it by set of smaller volume, but this function is decreasing. So I want to find points. This is sum of xi equals 1. Here sum of xi equals 1 plus gamma. I want to cover this simplex by points here under condition that I have some inequality for coordinates. So each point covers here intersection of this segment with such coordinates. So it's not difficult to see that in fact I need to cover simplex by minus simplex. So if I produce better picture, d-dimensional simplex, d minus 1 dimensional simplex, which is here, I need to cover by smaller minus simplexes. And such bounds are known. So we will apply some results from convex geometry, high-dimensional convex geometry, and we'll get bound. And this is first step, and second step I probably will skip. So here I considered only anchored boxes, but then I will shift this to all places. So I need additional nets of shifts. And then I will cover all possible boxes here. This is essentially construction. Of course, I need to check that everything works. So here are some calculations, which is probably not a good idea to show here, but you should believe me that everything works. So this was idea of the construction of boxes. And it's, like I said, this is pretty sharp construction, especially that our result, in view of previous result for random points, is sharp up to double logarithm of 1 over epsilon. Now I still have time, so I will very briefly say about case of large epsilon. Large, well, here large is larger than essentially 1 over d. So in Sosnovets and Mario result with Jan Wiberl, they use lattice, and somehow it was, actually some people say that lattice works better than Lebesgue measure, which was extremely surprising for me. And the question was why it's better. It should be the same. And at least, in my opinion, the only difference was that whenever you use lattice, of course, you don't take points on the boundary. You consider lattice inside. So, so the only difference, at least from my intuition, it was that lattice guarantees that you don't have points on the boundary. Well, if you use Litvak measure, then there is huge concentration around boundary. So this was difference, but we can adjust distribution. So we can use Litvak measure, but guarantee that with some adjustments that you are not on the boundary. And this, so this gave bounds that I already mentioned, which improved by just 1 power of logarithm. But more important that we can use Litvak measure also here, and to have random points, and how to adjust. Just whenever I have random point, it's product probability, so I need just to understand how points are coordinates distributed on a segment. So what we will do, we will put this is segment 0, 1, we put epsilon here and 1 minus epsilon here. And if my random points falls down here, it will stay. But if points comes here, I will move it to the boundary, to the epsilon. If points comes here, I move it here. So essentially this distribution, this adjustment of Litvak measure works and gives the result. So formally it's written here, the functions that we use. And why it helps also, because of second argument here is that whenever I have box of volume epsilon, volume of box is product of lengths. It's essentially a step why I need large epsilon, relatively large with respect to dimension. Because if product here is larger than epsilon, I know that not many of them, it's impossible that many of them are small. So if we consider increasing rearrangement of them, then because we have this bound, for any j which is larger than m, which is exactly this number, say integer part of this, we have bound which is larger than, that length is larger than 1 minus epsilon. But then in such coordinates I don't need to approximate, because if my point fall down here and length is larger than 1 over epsilon, it is inside the segment. So essentially I don't need to approximate segments inside my box whose length is larger than 1 over epsilon. And it essentially decreases dimension to this dimension, because I don't approximate other coordinates. And then, of course, you need to multiply by all possible choices because you have rearrangement. But essentially, you apply previous results to dimension m, and then you get the result. So I probably skip calculations because I want to make just one remark on the torus when we consider not only segments, well, standard segments like this, here is AI, BI, but also such segments. So AI is larger than BI, so we take this part and this part. So we just pass to torus and ask exactly the same question. Then just combining results of Mario, who proved lower bound, and Rudolph again in the same paper, we have such bounds. Now it's already cannot be obtained from this paper because we see dimension of of rectangular boxes on the torus is higher. It's larger by logarithm, so we cannot apply what they prove unless we are losing logarithm in Z. So this was proved, and from our paper once again this term we have the same. But here we can substitute with double logarithm. Once again, it's not for random points, but if you want random points, then from paper of Livgala Lifshitz, we have this term logarithmic, which is unavoidable if you deal with random points. So I will stop here.
Okay. Any questions or remarks?
You said that you did not want to cover any of those construction models to build this point. But still, which methods are there? Are there any new methods how to build constructive points? Because you know methods which go from algebra, you know some methods which go from number theory, and more or less that's it. Do you have any suggestions?
Yeah, I don't know. I say that I don't want to mention, not that I don't want to work on it, but I don't want to mention in this talk some papers because it's huge literature. But Buchau and previous results that I mentioned, they use algebraic construction quite heavily. Buchau, well, they use lattice points, but at some point they also apply random choice on these lattice. Like actually in Ulrich Wibral, they also use lattice points, but they choose randomly what points to take. So, and Buchau has actually two steps. But I don't know how to improve these results using classes.
Okay, some please.
Just a comment to that. There's the second work of Jan and myself where we make deterministic constructions based on error correcting code.
Yeah, but does it give better result?
Not better result, but
okay.
It asks for other constructions. That
yes.
Error correcting code
Yeah, there is your result, there is David Crick also some construction, but still I don't see how to use to improve power.
But this, about your question, it's a well-known fact from 50s, last century, that the lattice is good at, for multidimensional integration. Your problem is connected, closely connected. So the Korobov nets and some other lattice net very well work. Okay.
No, I wanted actually to ask this question. What is the application of this result, or whatever connection with integration or something like that? So what these results are needed for?
Well, I don't know too many applications because some
is
people argue
classical
that
topic.
it's classical topic in approximation. There were some works, I think by Eric Novak and somebody with approximation of one-dimensional tensors. This old paper that I mentioned, four authors, they argue that it's important in statistics, but then two-dimensional case. So, because you have two parameters and you need to understand what is good, but I don't know to me.
Most classical problem closely connected with this topic is problem about discrepancy.
Yes, it's dispersion, of course, lower bound for discrepancy.
Okay, so if short question exists, please.
I just want to ask, what happens if you take in the definition just diagonal rectangles?
What?
In the definition of n epsilon d, you consider only diagonal rectangles.
No, the answer I don't know, but I think the first paper, first one that I mentioned, they used dyadic numbers, so it should give, but this one was d to the d, which is not good. I don't know. I don't know.
Situation, or you don't know?
No, I don't know.
Okay.
I know that bound d to the d over epsilon will work, but it's not so good bound.
We should go, stop here. I'm sorry, but let's thank speaker again.